Hi there, folks. Today we're looking at adding and subtracting polynomials, and really we'd already know a little bit about this in terms of combining like terms and adding those things together, but we're going to add to that a little bit. We're going to expand it out to polynomials. We're also going to identify polynomials in terms of their degree and that kind of thing, and some of the naming protocols that are behind some of this. So the first thing we're going to look at is a monomial. A monomial is a real number, a variable, or a product of real numbers and variables, all right? It's basically a single term. And single terms are anything that are kind of a conglomerate of multiplication. And so that's what we have here. Terms are separated in polynomials by addition and subtraction. So this one, there is no addition and subtraction. It's one single term. It's one single group of multiplication, all right? The degree of a monomial is equal to the sum of the exponents of its variables. We don't look at the exponents for the number. We only look at the exponents for the variables, and we add them together, all right? So a single monomial, a grouping of multiplication of numbers and variables, we find its degree by adding up all the exponents, all right? For example, if I look at something like this guy, this is a monomial because it's a single term. It's one grouping of multiplication of a couple things, and so we kind of consider it together, all right? And so this is one term. The degree of this monomial, I just add up the exponents, but only for the variables. Well, since there's only one variable here, all I have is the 5, so the degree of this one is 5. Okay. If I look at the next one, again, it's a monomial. Even though you can clearly see like a 2, an A, and a B, we can kind of see those separate pieces. It's one term because it's all multiplication, all right? When they're combined by multiplication here, when they're together in terms of multiplication, we consider it one term. Terms are separated by addition and subtraction. So multiplication, it's all one term, all right? So this is a monomial, and if I want to know the degree of that monomial, I add up the exponents, but only for the variables. So when I look here, I've got a 4 and a 3. Well, that's a 7, so this is a degree of 7. And it makes sense, really, when you think about rules of exponents. When you multiply, you add the exponents. Well, I'm just trying to get a sense of the number of exponents listed here. And since it's multiplication, I add the exponents. Now, granted, not from the perspective that I have the same base, so I add them together. I can't add them. But when I look at the degree, it's kind of applying that same rule of exponents, if that's an easy way to remember it. Multiplication, I'm adding the exponents for the degree. Okay? And then if I look at this one, this is still a monomial, even though there's no variables here. That's okay. It's still a single term, so it's a monomial. But now I add up all the exponents for the variables. And since there are no variables, we would say this one has a degree of 0. And the other thing you can think about here, once again, going back to rules of exponents, let's say I added a variable here. Let me put an x. It would have to be an x to the 0 power, because x to the 0 power is 1. 1 times 7 is just a 7, all right? So anytime I have a single number all by itself, I could put as many a to the zeros or x to the zeros or b to the zeros as I wanted, because those would become 1s, all right? And in terms of multiplication, wouldn't change anything. That's why it's a degree of 0. We can always say there's a variable to the 0 power there, even though it's not written, okay? Just like when we have invisible ones, a variable to the 0 power is an invisible one, so it's a degree of 0, okay? Like terms, still talking about the exponents on these things, monomials containing the same variables with equivalent exponents. So if all the variables are the same and all the exponents on those variables are the same, then we have like terms. And so if I look at something like this one, 4x to the 10th and 5x to the 10th, yes, those are like terms because the variable and the exponents on those variables are the same. So I would say, yes, these are like terms. Okay? If I look at the next one, I've got a 3xy to the second and a 6x squared y. And so as I look at this, I have the same variables, which is a good sign, but each of those variables do not have the same exponents. Look at the exponents and how they're delineated here. So like here, x to the first, here y to the first, maybe if including those would help. And so as I look at this, it's the same variables, but in the first one, the x variable has an exponent of 1, and the second one has a variable of 2, or an exponent of 2. The first one has a y to the second, but the second one, the y's to the first power. See, the variables match, but their exponents don't. All right, and if the exponents don't match, then this thing is not, these are not like terms, so no. Okay? And then if I look at this one, 4x to the third y, 5x to the third y. Once again, the variable is the same. I have x and y for each, and their exponents match. X to the third, y to the first, y to the first. So the variables and their exponents match. So yes, these are like terms. Okay, and it's important to be able to identify like terms because we need like terms in order to do addition and subtraction. So adding, subtracting monomials. If I have just a single term, they have to be like terms. This only works if they have like terms. So monomials can only be added or subtracted if they are like terms. And to do the addition or subtraction, I add or subtract the coefficients and I leave the variables the same. All right. And you probably already know this. We've done a lot of simpler examples like, a 5x plus a 10x is a 15x and the x stays the same. And, when you think about rules of exponents, it makes sense that when you add or subtract, you don't do anything with the exponents. They stay the same. I need like terms, and those like terms stay the way they are. The variables, the exponents stay the way they are. For example, if I look at this guy, 4x to the 10th plus 5x to the 10th, those are like terms because they have the same variable and the same exponents. So because they're like terms, I can add them up. I just do the 4 plus 5 is a 9. And then the variable part stays the same, 9x to the 10th. Okay? If I look at the next one, I've got a 3xy squared minus 6x squared y. Before I do anything, I have to make sure these are like terms, and these are not like terms. The variables match, but their exponents don't. Okay, I've got an x to the first and an x to the second. I've got a y to the second and a y to the first. The variables don't match. I cannot add these together. These would have to stay the way they are. Okay, they have to stay separated. I cannot do the subtraction because these are not like terms. Okay? If I look at this guy, I've got 4x to the third y minus 5x to the third y. And once again, the variables match. The exponents on those variables match, so these are like terms. So I subtract 4 minus 5 is a negative 1. And then the variable part stays the same, x to the third y. I could clean that up and say negative x cubed y. I can make that 1 an invisible 1. And now I kind of crossed out my 3. That was a terrible box. There we go, much better. Okay? If I look at this guy, this is an example we're really used to. And again, if you don't see a coefficient here, that's a 1. So this is an x to the first and x to the first. The variables and their exponents match, so these are like terms. 1x plus 3x is a 4x. And it's essentially like saying how many x's do I have? How many of that variable, those like terms, do I have? Here, 3y squared minus 6y squared. These are like terms, so I subtract. That's a negative 3y squared. The variable part stays the same. This one, x cubed y and x cubed y, the variables and exponents match. These are like terms, so I subtract. That's a 2. And then the variable part stays the same. Okay? Polynomials is a monomial or a sum of monomials. So basically, again, a monomial is a single term. Terms are separated by addition and subtraction. So when we talk about polynomials, polynomials are just a bunch of terms separated by addition and subtraction. Okay? And so it's a sum, a monomial or sum of monomials. Even a monomial, we can still call it a polynomial, all right? But it has a special name of monomial, all right? We do have a couple special names. We've already talked about monomials. Two terms would be called a binomial, like a bicycle has 2 wheels, so that idea of bi meaning 2. A trinomial is 3 terms, so if there's 3 terms, it's called a trinomial. Again, tri, like a tricycle, meaning 3 wheels, so tri meaning 3. And so we have some of those special names. Those are the ones that we use the most often. All right, 1 term is a monomial, 2 terms is a binomial, 3 terms is a trinomial. Okay? Let's talk about the degree of these things. The degree of a polynomial is basically whatever the biggest monomial degree is, all right? So when you think about it, again, a polynomial is made up of monomials being added together. And so if I look at each of those terms, each of those monomials, and I find the degree of each term, the degree of each monomial, the degree of the polynomial is just whatever one of those is the biggest, okay? So the degree of a polynomial is equal to the degree of the highest degree monomial term, all right? So I'm just going to look at each term separately and say, what's the degree of this term? What's the degree of this term? What's the degree of this term? Whichever one of those is the biggest, that's the degree of the polynomial, okay? The other thing we're going to look at here, and it's not listed, is something, the leading coefficient. because that's an important value that we use in a lot of other applications, but it also gets us in the habit of writing these properly. So we'll do that as well, okay? For example, if I look at something like this guy, again, I just look at each of these terms individually. And again, terms, the monomials are separated by addition and subtraction. So here's the first term, here's the second term. So this one right away, because there are two terms, this is a binomial, okay? And if I want to know the degree of this binomial, I just have to look at each of those terms individually. Say, hey, the degree of this term is a 5 because the exponents for the variables add up to a 5. The degree for this term is a 1 because the exponents on that variable add up to a 1. And if one of those terms had more than one variable, again, to find the degree of a monomial, which is what each of those terms are, we add up all the exponents from the variables. Okay? The reason we don't add up the 5 and the 1 here is because those are separate terms. Okay? If I had multiple exponents for one term, I would add them up because that's a monomial. But then for the polynomial, I'll just look at each term individually. Okay? And so for this one, the biggest term that I see, the biggest degree term is 5, so the degree of the polynomial is 5. Okay? I just take whichever one is biggest. And so here's how I'm going to list this. I'm going to list a couple different things here. So I'm going to list this particular example, I'm going to list it as a binomial. I'm going to call it by the number of terms first. And you don't necessarily have to follow this exact naming protocol. We'll do something different in the next one. But I'll call this one a binomial of the 5th degree. And see, that kind of gives this thing a label and name in terms of the number of terms and the degree. But then I'm also going to list one other thing, and it's not something I necessarily asked for so far here, but I'm going to list the leading coefficient. So a binomial of the 5th degree with a leading coefficient, which I'll abbreviate as LC, of, and the leading coefficient, leading means out front, and the coefficient is always the thing in front of a variable. So the leading coefficient is right here. It's the 1. It's the coefficient that's kind of paired up with our x to the 5th power here. Okay, so it's a binomial of the 5th degree with a leading coefficient of 1. And the leading coefficient becomes a kind of an important thing when you're looking at graphing and those kind of things. There's a lot of functions that the leading coefficient tells us a lot about those functions and what the graphs look like and how they act and how they respond. Okay, so the leading coefficient is important from that regard. It's also important, though, because we want to list this thing in the appropriate order. When we list a polynomial, standard form for a polynomial is always listing it in descending order in terms of our exponents, okay, in terms of our degrees. And so back to this idea that as we look at each of these terms, I had a 5th degree term and a 1st degree term. Well, I want those listed in descending order, in other words, from biggest down to the smallest. And so when you look at this particular example, this one's written properly. I've got an x to the 5th followed by an x to the 1st. They're written in descending order. And that's how we want to write these things, okay? So keep that in mind. So this one, binomial of the 5th degree with a leading coefficient of 1. We could have also said a 5th degree binomial with a leading coefficient of 1, which is typically how I tend to say it, only because I think that uses a little bit less in terms of words. But again, as long as you understand, hey, this is the type of polynomial it is, this is the degree of the polynomial, and this is the leading coefficient, all right? Applying the same thing to the next one, if I look at this next one, right away, let's identify the degree of each term. And so as I look at each of these terms, here's my first term, and that has a degree of 2. Here's the next term, and that has a degree of 4. And here's the last term, and that one has a degree of 1. And so right away, before we even decide what the degree of this polynomial is, I mean, we can tell what it is. We just pick the biggest of these values. But right away, I should notice that this thing is not written in the proper format. It's not written in descending order. Okay, I should have this listed from biggest degree down to smallest degree. All right, and so if I were to rewrite this one properly, I would have to write the negative 3x to the 4th first, followed by the 9x squared, and then the plus 8x. See, now this thing is written in descending order. Now it's written appropriately, okay? And so now I can kind of look at this thing and determine, hey, what type of polynomial, what's the degree of the polynomial, and what's the leading coefficient. And so as I look at this one, I'm going to do this one a little bit differently this time. Last time I said binomial of the fifth degree with leading coefficient of 1. This time I'm going to start with the degree. I'm going to say this is a fourth degree, okay? Because again, I look at each of those terms individually. I take the biggest one. So this is a fourth degree trinomial this time. And that's with a leading coefficient of -3, okay? And it's really important that you understand that it's a -3 because I had to write it correctly first. I had to put it in standard form in descending order first, and now I can see the number that's supposed to be out front, okay? So the leading coefficient of this one is -3. I had to write it properly first, okay? So adding and subtracting polynomials. Step 1, if it's subtraction, I would change it to adding the opposite. You could also think of that like distributing the negative sign. You could go through and subtract each of the like terms, but we're just asking for the mistakes. We're asking for headaches when we do that. Change subtraction to adding the opposite. Distribute that negative, if you like to think of it that way. Then combine like terms, okay? And a little typo there. Combine like terms, okay? So for this one, I've got a 3x squared minus 2x plus 8. I've got a 2x squared plus 5x minus 3. Those are two trinomials. So I'm adding two trinomials together. And I just have to identify like terms. I can only add the like terms. And so when I look at this, these are like terms because they have the same variables and the same exponents. So I can add those terms together. That gives me a 5x squared. Remember, I add the coefficients. The variable part stays the same. These guys are like terms. Negative 2x plus a 5x. And yeah, make sure you include the sign with that 2x. That gives me a plus 3x. Again, the variable part stays the same. And then these guys, the numbers at the back here, the 8 and the -3, those are like terms. So I add them together, and that's a plus 5. And that's it. So here it is. I added these two trinomials together, and I add them simply by combining the like terms. Okay? If I look at the next one, this is subtraction this time. And here's what I would do. I would change subtraction to adding the opposite. So I'm going to change subtraction to addition right here in the middle. But now I have to do the opposite of that second binomial. Well, the opposite means I have to do the opposite of each of those terms. So I would make this a negative 6x and a plus 2y. Plus 2. Sorry, there's no y there. All right. You can also think of this as I've just simply distributed the negative sign. And since the negative sign's not out front anymore, it's a plus sign out front. But again, we're changing it to adding the opposite. So now I combine like terms. When I look at this guy, there is no like term for the 2x squared. There is no other term here that has an x with an exponent of 2. So that one, there's nothing I can add to it. It stays the way it is. Okay? We don't get rid of it. It's still there. It just hasn't been changed because we haven't added anything to it. Okay? These guys, these are like terms. So the 5x and the minus 6x is a negative 1x, so a minus x. And then this guy, the 1 and the 2, that's a 3. Okay? If I look at this one, same kind of thing. I've got two trinomials being subtracted this time. Let's change that subtraction to adding the opposites. Instead of subtraction, I'm going to do addition. And now I have to do the opposite of everything that's in here. Okay? So instead of a positive 2, it's a negative 2. Instead of a plus 5, it's a minus 5. Instead of a minus 3, it's a plus 3. Okay? Essentially, I'm distributing that negative. I'm changing that to a plus, which means the negative gets distributed. Okay? And now I can combine like terms, the 3x squared and the negative 2x squared. Those are like terms. So that gives me a 1x squared. The negative 2x and the minus 5x gives me a negative 7x. And the 8 and the 3 give me a plus 11. Okay. If I look at the next one, again, combining like terms, it's addition, so I don't have to worry about changing any signs. I just have to combine like terms. And so here, the x to the third, there is no other x to the third. So there is no like term. That one just stays the way it is. There's nothing I can add to it. Okay. The x and the 4x, I can add those together. That's a 5x. And then the minus 7, there's nothing to add there, so it just stays as a minus 7. Okay. So again, When we're looking at these things, degree of a monomial term, we add up the exponents for the variable. Degree of a polynomial, we look at each term individually. We find the degree of each term, and then we just take the biggest one, okay? And then adding and subtracting, subtraction changes to adding the opposite, but then the idea is to just combine like terms, okay?